All right, welcome to Math 1314, our very first section for guided notes. You will want to actively complete these guided notes. Listen along to the video while you fill in your copy. Don't do it while you're watching your show in the background or listening to songs that distract your attention. Pause as we go through, stop and rewind. You get to control the speed of the lecture this way. All right, we're starting out focusing on quadratic equations, and we're going to start with our definition. A quadratic equation is a second-degree polynomial, and that word polynomial just means many terms. So we have one or more terms, and second degree. Second degree means the highest exponent is a 2. The graph of a quadratic equation is always going to be a parabola or a U shape. Now my general form of my quadratic equation is going to be ax squared plus bx plus c equals 0. General form, I have all three terms on one side set equal to 0. And this is true where those values a, b, and c are all real numbers, not imaginary numbers. And a is not 0, because if a were 0, that would make our squared term go away and it would no longer be second degree. The second degree is determined by this being the largest exponent on a variable. So x is my variable, a, b, and c represent values. Okay, no matter what quadratic equation I'm given, that graph is always going to be a parabola. It's going to be a U shape. What might that parabola look like? Well, we're going to focus on some graphs of parabolas with x-intercepts where we cross the x-axis. X is my horizontal axis, y is my vertical axis. And the zeros, that's just another word to represent x-intercepts. X-intercepts, zeros, or sometimes we refer to it as the solution for our equation. It's possible that we might have one x-intercept. Now that can happen if the parabola is sitting on the x-axis. It can open up or down. This is my parent function for my parabola, y equals x squared. My x-intercept here is also the vertex 0, 0. Vertex and the x-intercept are the same point. They're sitting at the origin 0, 0. Another option, if my vertex is down here and the parabola opens up, or if the parabola was upside down and the vertex was high and it opened low, I'm going to have more than one x-intercept in that case. There's my x-intercepts right there. My vertex I took care with. My vertex fell at 0, -2. Those x-intercepts I didn't pay very close attention to when I was sketching my graph. They're kind of falling in between 2 points. So let's say my x-intercepts here fall at -1.5, 0, and +1.5, 0. Another option might be that, like I said, I have a vertex that's up above, and then I have my parabola opening downward. I paid more attention this time to my x-intercepts. I have two x-intercepts again, right there where I cross the x-axis. This time I put my vertex at 1, 3. That's where my vertex for my parabola is. The vertex is either the highest point or the lowest point of the parabola. And my x-intercepts fall at -1, 0, and +3, 0. Now if you start looking at these ordered pairs, you'll notice that the thing they all have in common is that my y-coordinate in my xy ordered pair is 0. That's what happens when I'm on the x-axis. And then another option might be that I have a parabola whose vertex is down here and it opens down. Or maybe the vertex is up here and it opens up. Well, for this one, I have a vertex at -2, +2. And for this one, I have a vertex at +2, -2. But because of the direction both of these separate parabolas are going, my x-intercepts are imaginary. They're not real. No real x-intercepts. Anytime I have imaginary solutions, when I set my equation equal to 0, those solutions don't show up on my graph because my graph is a real number coordinate plane. Okay, when we're working with quadratic equations, there are 4 basic ways to solve. When we solve a quadratic equation, we're looking for those x-intercepts, which happens when y is equal to 0. Sometimes our solutions are imaginary, just like this last example I gave. Imaginary solutions don't show up on our graph. Okay, our most basic way to solve a quadratic equation is by factoring. Usually you're going to find a common factor first. Always, always, no matter what type of equation you're factoring to solve, you want to look for a common factor. If you can't solve just by finding a common factor, then we're going to do what we call reverse FOIL. FOIL, hopefully you remember FOIL from a previous course. FOIL is how we multiply together quadratics, and it stands for first, outside, inside, and last. Alright, let's focus on this first step. If I'm going to factor by solving, my first step is always going to be to set my equation equal to 0. That's my first step. Set my equation equal to 0. So I get it in that general form where I've got everything interesting on one side, 0 on the other side. So I'm going to set my equation equal to 0. My first example for solve by factoring, we're going to do 2x squared minus 7x equals 0. Now I know this is quadratic because it's a second degree polynomial, but when I compare this to my general form, I see that I only have 2 terms, not 3. I don't have that constant. So I want to see if I can just factor out a common factor. Well, the thing that both of these 2 terms have in common is an x. So I can factor that x out, and what is left behind is 2x minus 7. If I multiply this x back through, x times 2x is 2x squared, x times -7 is -7x. That's still equal to 0 because we're solving an equation. Now my zero factor property tells me that if I'm multiplying 2 things together and the result is 0, that means at least one of those has to be equal to 0. So that's what I do for my next step. I set both of those terms, both of those pieces of information equal to 0. Well, 0 equals 0, that's done. There's nothing else to do there. I need to finish solving for x here. So I'm going to move that 7 over by using the opposite operation. This is 2 times x. The opposite of division or multiplication is division, so I divide both sides by 2, and I get x equals 7/2. So I had a second degree polynomial, a quadratic, and I got 2 real solutions. Okay, let's look at another one. For this one, I'm going to give you one that has all 3 terms. So x squared equals 8x minus 15. I know this is quadratic because it's second degree. My first step to solve is going to be set the equation equal to 0. So that's where I go next. I'm going to keep my squared term positive, so I need to move everything else over here to the left. So I'm going to subtract 8x from both sides and add 15 to both sides. So subtract 8x, add 15. That gives me my quadratic equation in general form set equal to 0. Alright, I don't have a common factor I can factor out, so we are going to reverse FOIL. To multiply this together, if it will factor, I'm sorry, it had started with 2 binomial factors, 2 terms multiplied together. So we're going to reverse that and think about how we would have multiplied it together to get this to start with. well, my first I'm sorry, my screen just clicked off and I wasn't sure if I lost the video or not, but I think we're still here. My first term is x squared. To get x squared, I had to multiply x times x. Now, I see that I have a positive constant here. That positive constant tells me my last product, those signs had to be the same. I know the signs are going to be the same, and so I look to the middle and I see that this middle term is negative. That means both of these have to be minus, x minus, because a negative times a negative is going to give me that positive 15. Now I need factors that multiply together to give me 15, and the factors need to add up to get me to 8. Well, 15 can be 1 times 15, or it can be 3 times 5. Those are the only integer factors that 15 has. And the pair of those that add together to get me 8 is 3 times 5. So let's think about foiling this back together to check and make sure we got it right. X times x, that's my first product, that's x squared. My outside product would be x times negative 5. My inside product would be negative 3 times x. So I have a negative 5x and negative 3x. That goes together to give me the negative 8x. And the negative 3 times negative 5 is my positive 15. So we factored it correctly. Just like over here, after I get my factors, I use my zero factor property, set each of those factors equal to 0 to see what would make my equation true. Well, x minus 3, the opposite of subtraction is addition. So I use that opposite operation to move that constant to the other side and get my solutions. So my solution set here is going to be 3 or 5. Those are the two values that I can plug in for x and make this a true equation. Okay, let's look at our next page. Oh dear, sorry. Sorry guys, this did front and back and I thought it was front side only. Here we go. So when the second x, the x term is missing, we're going to use our square root property. Our square root property tells me that for any real number k, I take that squared term equal to k, and I'm going to solve its equivalent to using the square root to both sides. Now when I take the square root of both sides, so let's go ahead and do this. Let's show one more step here. If I have my x squared equals k, I can take the square root of both sides. Now the opposite operation here, squared and square root, opposite operation. The thing is, since I don't know if this value k started as positive or negative, it gives me two solutions. So I have to consider that that square root k, that square root k could have started out positive or negative. So square root of a square is just x, and that's going to be the positive and negative square roots of whatever that constant was. So remember, when you take the square root to solve, you always have to consider that it could be plus or minus. You've got to get those two values in there. All right, my first step, and I was going to try to color code this the same way. My first step is going to be to set the squared term equal to the constant. Squared term equal to the constant. My first method, solve by factoring, my first step was to set the equation equal to 0. My first step here, when I'm using my square root property, is to get the squared term equal to the constant. Let's do two examples here. The first example we're going to do x plus 2 squared minus 25 equals 0. Well, I've got a squared, something squared, and I've got a constant. I need to set that squared term equal to that constant. That's my first step. So x plus 2 quantity squared, if I add that to move it over, that becomes equals of positive 25. Now to undo the square, I take the square root of both sides. Always when I'm solving equations, I do the golden rule of math. Do unto one side what you do unto the other. So if I take the square of both sides, I have to remember that whatever got squared, positive square root of 25 or negative square root of 25? Well, 5 times 5 is 25. Negative 5 times negative 5 is also a positive 25. So square and square root cancel out and leaves me with x plus 2 equals, like I just said, plus or minus 5, because the square root of 25 is 5. Now this plus minus tells me I have two different equations I need to work with now and solve. I've got x plus 2 equals positive 5, and I have x plus 2 equals negative 5. So for each of these equations, I need to move that 2 over. I have plus 2. The opposite of adding is subtracting 2. So I subtract 2 from both sides. I get positive 3 here. And when I subtract 2 here, I get x is a negative 7. So that's my two solutions. I don't mind you leaving them separate. My math lab, I think, usually has you put them in fancy braces. All right, one more example for square root property. Let's do 5x squared plus 1 equals 51. I know this is quadratic because it's squared. I've got a squared term and I have constants. Let's clean that up as much as we can. We want to set it so that our squared term is equal to our constant. Well, that first thing I'm going to need to do is move that 1 over. So I have all of my constants on the other side. So I've got 5x squared is equal to 50. Well, what are we going to do about that? This is not just my squared term. My step is to set the squared term equal to the constant. 5 isn't being squared, just the x. So I need to finish cleaning this up. And to clean this up the rest of the way, I'm going to divide out that coefficient 5. 5 times x squared, the opposite operation is to divide. 5 divided by 5 is just 1. So I have x squared equals 10 now. Now I've got my squared term in my constant, so I can undo that square by applying the square root property. When you take the square root, remember, plus minus. So I have x is equal to, well, 10 does not simplify. Positive and negative square root of 10. That's my two solutions. I can live it just like this, or I can write them separately as negative square root 10 to positive square root 10. Now notice that for each of these quadratic second degree polynomials, we have gotten two solutions. That is something that you're going to notice is a pattern that continues for the rest of our semester. All right, so that's two ways. Now the last two ways are when you have a trinomial, 3 terms that can't be factored. You have two different choices for how to solve. You can either complete the square, or you can use your quadratic formula. Both of these are things that you're going to do when you have all 3 terms and it can't be factored. Now, if I'm going to complete the square, you have to have a coefficient on the squared term that is 1. If your coefficient on the squared term isn't 1, you can't complete the square. Completing the square means I'm going to create a perfect square trinomial, and then I'm going to use the square root property on that perfect square trinomial. Now these are my two patterns for the perfect square trinomial. I gave you that as my first step. If you start out with a plus b quantity squared, this is what a perfect square trinomial looks like. If you start with a minus b quantity squared, this is what the perfect square trinomial looks like. Notice that when I compare these 3 terms, the only difference is the sign on that middle term. And that sign on the middle term is going to match the sign in the factor. Okay. So let's do a couple of completing the square. The first one we're going to look at, we're not going to solve, we're just going to complete the square. We're going to see what that pattern looks like. So I'm going to give you the first 2 terms, x squared plus 7x, and we want to complete the square. We want to see what that constant needs to be that's going to complete the square here. Now I know when I factor it, I'm going to get something plus something, quantity squared as my factor, because I've got this middle term plus. My step for completing the square is to identify, you've got ax squared plus bx, and we want to create c to complete the square. This value b is what we're interested in. To complete the square, we take half of b, and then we square it. Okay, you take half of b and you square it. Well, b is 7 here. Half of 7 is just 7 halves, and I'm going to leave it just like that. Then I square that, 7 halves squared. 7 times 7 is 49. 2 times 2 is 4. That is half of b squared. This is a perfect square trinomial. All right, now to use that perfect square trinomial and to factor it back out, I am going to break it apart. Think about reverse FOIL. Well, x times x gives me x squared. This second term here is always going to be whatever half of b was. Well, for this one, half of 7 was 7 halves, and it's a positive 7 halves. So it is plus 7 halves plus 7 halves. That's how this perfect square trinomial breaks apart into factors, and these factors are identical. So I get to write them as a single binomial being squared. So this is my perfect square trinomial, and my perfect square trinomial factored gives me two identical factors. That's what we're doing when we complete the square to solve an equation. Okay, let's do one. Completing the square to solve an equation. Let's do x squared plus 6x minus 11 equals 0. All right, if I want to factor this, my signs are going to be different. One would be plus, one would be minus. 11, factors of 11, the only way to multiply and get 11 is just 1 times 11. And the difference between 1 and 11 is not going to be 6. So this is not factorable. I'm either going to have to complete the square or use the quadratic formula. Since my coefficient on my square term is 1, I can complete the square. So I'm going to start out by moving the constant out of my way. When I move the constant out of my way, I leave space to complete the square. Now it's equal to 11. Whatever I add in to complete the square on the left, I have to add that same amount in on the right to keep my equation balanced. So now let's look at our steps. We're going to do take half of b and square whatever that was. Well, b is a positive 6. Half of 6 is 3. And I need to square my 3. I take half of b and I square it. Well, 3 squared is 9. So I'm going to add a positive 9 to both sides of my equation. If I add it on the left, I have to add it on the right to keep everything balanced. So now I have equals 20. 11 and 9 is 20. Over here, I've got my perfect square trinomial. It breaks down into those two identical factors. My first term, x squared, the square root of x squared is x. My last term is going to be b squared. The square root of b squared, the square root of 9, is 3. And I know it's a plus 3 because that was a positive. My value for b was positive. So now I've got my squared term equals a constant. This is the situation that I started out with when I'm using my square root property. That's what I'm going to apply here is my square root property. So to unsquare something, I take the square root. When I do something to one side, I have to do the same thing to the other. So I take the square root of both sides, considering plus or minus. Square and square root cancel out, leave me with x plus 3. That's equal to the positive and negative values of the square root of 20. Now, 20 is not a perfect square, but it has perfect square factors. Let's work on that over here. 20 is the same thing as 4 times 5. And 4 is a perfect square. So let's look at square root 4 times square root 5. What is my square root of 4? What do I multiply together times itself to get 4? Well, 2 times 2 is 4. So this bit simplifies to be 2. So this is equal to 2 square roots of 5. Square root 20 is the same thing as 2 square roots of 5. positive or negative, so I have to finish solving by setting it up both ways. X plus 3 equals a positive 2 square root 5. X plus 3 equals a negative 2 square roots of 5. And then I finish solving by subtracting that 3 and moving it over. Now I cannot combine my negative 3 with my 2 square roots of 5 because they are not like terms. So those are my two solutions here, and that I'm done. That's as far as I can go. All right, our very last way to solve quadratic equations. We had solve by factoring. We've got use the square root property. If we can't factor, we can either complete the square, which allows us to go back and use the square root property, or we use our quadratic formula. Now you need to memorize your quadratic formula. Your quadratic formula tells me that x equals negative b plus or minus square root of b squared minus 4ac all over 2a. Now this uses a, b, and c from our general case, our general form for our quadratic equation, ax squared plus bx plus c equals 0. That's what I'm using to get my quadratic formula values from a, b, c. Whereas when I use the completing the square, my coefficient of that squared term had to be 1. For a quadratic formula, that value a does not have to be 1. It can be anything. Now, the quadratic formula is super useful for us. Not only can we work all the way out and solve a quadratic equation using the quadratic formula, but we can predict if we're going to have 1 or 2 solutions, and if the solutions are going to be real or imaginary. We can predict generally what our graph is going to look like, how many x-intercepts, zeros, or solutions we're going to have. All those terms mean the same thing, based on the discriminant. Now, my discriminant is this bit that's underneath the square root. So my discriminant helps us discriminate what type, I'm sorry, let me write that neater. The discriminant helps us decide or discriminate or pick apart and predict what kind of solutions and how many. Discriminant, b squared minus 4ac. So I work out b squared minus 4ac, and it tells me what kind of solutions I'm going to have. Now, when I solve this, when I plug in numbers and figure this out, that number, that value that I get is either going to be 0, it's going to be positive, or it's going to be negative. Those are the only 3 options I have: 0, positive, or negative. If I work out b squared minus 4ac and it's 0, this square root part goes away, that plus minus goes away, and I'm left with negative b over 2a as my solution. That is real, and it's just one solution. That's one real solution. If I work out b squared minus 4ac and it's positive, well, the square root of a positive number is a real number. So it's going to be real solutions, and I've still got that plus minus there, so I'm going to have 2 of those real solutions. But if it comes out to be negative, the square root of a negative number is what we call imaginary. It's non-real. So if this is non-real, it still exists, which means I'm going to have 2 of those non-real or 2 imaginary solutions. Okay, our last thing we're going to do is going to work through one of these quadratic equation problems so that you have an example in your notes. Our first step when we are doing our quadratic formula is to set our equation equal to 0 again. We want it in that general form, set equal to 0, so that we know our values for a, b, and c. That x is just ugly. Let me see if I can clean that up. There we go. Okay, let's do x squared plus 6x minus 11 equals 0. That's the one we just solved using completing the square right here. So we already know what our solutions are going to be, but we're going to solve it a different way. Now, we're going to use our quadratic formula. So we're going to pick out a, b, and c. A is 1, b is 6, positive 6, and c is negative 11. And I'm going to take those values and I'm going to plug them into my quadratic formula. So x equals, negative b means the opposite of whatever b is. That's going to be negative 6 plus or minus square root of b squared minus 4 times a times c, all over 2 times a. I'm just plugging into that formula, quadratic formula. Now my next step is going to be to simplify. I'm going to simplify underneath my radical. Negative 6 plus minus, well, my denominator, 2 times 1 is just 2, so that's easy. All right, underneath my radical, I've got 6 squared is 36. A negative times a negative is going to be a positive, so I'm going to add there. 4 times 1 times 11, that's just 44. Now, I look at this immediately, I see that my discriminant is going to be positive. So I know that I'm going to have 2 real solutions, which means my graph will cross the x-axis in 2 places. My graph is going to cross the x-axis in 2 places. So let's go ahead and finish working it through to get to those 2 real solutions. We've got negative 6 plus minus all over 2. Square root of 36 plus 44 is 100, right? No, sorry. In my head, I'm doing things that I shouldn't. 70, 80. There we go. 80. Not a perfect square. If it's a perfect square, we wouldn't have that radical in our answer. All right, so let's simplify our 80 as much as we can. Remember, we're looking for perfect square factors. I know that 8's divisible by 4, right? So a little bit of side work. 80 would be 4 times 20. And we just did 20 as 4 times 5. So 80 is 4 times 4 times 5. I can work with that. So underneath my radical, 80 is the same thing as 4 times 4 times 5. Well, what can I simplify? 4 is a perfect square, 5 is not. So that square root 5 is going to have to stay square root 5. I can't do anything about that. But square root 4 is 2. Square root 4 again is 2. 2 times 2 is 4. So I've gotten to negative 6 plus minus. 2 times 2 is 4 square roots of 5 over 2. That is not the look, that doesn't look the same as the answer I got when I did completing the square, does it? That's because I haven't finished simplifying yet. Finished simplifying. We always simplify as much as we can. So I'm going to come up over here because I ran out of space. I have an option. I can look at this as, okay, I've got 2 terms in my numerator, I can factor out a 2, or I can just split them apart because I've got 2 terms in my numerator, each of them is over that denominator 2. So I can take this rational expression and I can rewrite it as negative 6 over 2 plus minus 4 square root 5 over 2. Same thing, just written as 2 separate terms. Both of them have 2 as their denominator. And now I can focus on each term individually to simplify. Well, 6 divided by 2 is 3. Negative 6 divided by 2 is negative 3. And then I've got my plus minus. 4 divided by 2 is 2. So plus minus 2 square roots of 5, which is what I got. Negative 3 plus or minus 2 square roots of 5 for the solution on this equation on when I completed the square. So if I can't factor, I've got 2 options for solving, either completing the square or the quadratic formula. I can always use the quadratic formula. I can only complete the square if that coefficient on my squared term is 1.